Welcome to Building Practical Software as a Service with Python. I don't know who knows me, but my name is Armin. Armin Ronacher. I built Python open source software for the most part, and I have been doing this for a really long time now. I built the Flask framework and a lot of Python open source libraries. And one of the things that I'm doing for more than 2 years now is working on Sentry, which is also an open source project, but it happens to be a software as a service business. And it's almost entirely built on top of Python. So I want to go a little bit over how we do things there and why I think Python is actually a really good language for this sort of setup. So I built this, but it's not actually the foundation of what Sentry is, but it's the foundation of a lot of little services that people build, which build foundations to software as a service platforms. And it's one tool that you can use, but it's not necessarily the only tool. So Sentry, for instance, is almost entirely based on Django. I think at this point it's about 7, 8 years old. It's a Django application at its core. It's obviously also written in Python as a result of this. And one of the things that sets it apart a little bit from how a lot of people structure Flask applications is that it's one huge monolithic code base. And it's only now slowly being pulled into smaller bits and pieces. So I think this is very contrasting to how I used to do things before, which is building little smaller services and then combining them. And Sentry has sort of been the opposite. It's one huge service, which is slowly being broken up into parts. And it's for me, it was quite a contrasting experience to see the advantages and downsides of a monolithic design. So if you don't know what Sentry is, it's a crash reporting service. Essentially, you can hook it up with the application, and you will then get all your error reports sent into Sentry from the little agents that you have installed with the application. So it works with Python, JavaScript, and a bunch of native languages as well. And then it gives you a nice user interface. So and this is just a little bit more how it looks like. One of the interesting things about this is that it is an open source project, and this is sort of what I do. I like open source. And one thing that always comes up is how do you monetize open source? And I think the only real way in which you can do it is a software as a service. So as an extension of loving open sources, I really like the idea of software as a service as a way to monetize what you have, or generally just as a business model. So software as a service, what does it mean? The biggest and most important thing of it is it's multi-tenant, which means that multiple users are isolated from each other, and they have to utilize your platform. But at the same time, for a lot of users, that is not the only thing that they can support. So for instance, if you have a bank, banks often have regulations that they don't really have much choice in circumventing. So you also often have to look into supporting on-premise customers. And that's one thing that works really well with Python, to support both of those things at the same time. And I will go into this a little bit. Also, one thing that you can definitely see becoming more and more popular is managed cloud, where you go in, install your stuff on, and then manage the private cloud instance for your customer. And this is also works really well in the Python environment. So why do we use Python? Primarily we use Python, we as in Sentry use Python because it was already Python and there is no real reason to change it. So the decision to use Python was really made a long time ago, I think 7, 8 years ago. But why would you use it nowadays? And I think the real reasons why we use Python didn't actually change in the last years. Python has a very strong ecosystem, and I think that's still the reason why you want to pick the language. There's a lot of stuff in the language which just doesn't exist yet for other communities, or is not nearly as well maintained there. Then the iteration speeds that you have on Python are significantly higher than most other languages, while not sacrificing maintainability. And I think this is really important. The environment is very stable in comparison to particularly JavaScript. So we can actually deploy stuff and are quite confident that it's still going to look more or less the same in 2 or 3 weeks. It doesn't iterate nearly as quickly as other things. And then obviously you have a lot of very established programming languages like Java, which also have a stable environment, but which don't provide nearly as fast the iteration speeds. powerful metaprogramming, I think, is for us something that we can sometimes overuse, but the ability to introspect code, to modify it as it runs, is very, very nice. Just the ability to attach decorators and stuff is great. And because you have this interactivity on actually modifying code, like just changing language, changing functions and stuff like this, you also have the ability to just introspect the interpreter as it runs. And I think that's probably my personal favorite of what the language runtime provides, is the ability to inspect into it. And I think without that being a core element of the language, I think Sentry wouldn't have happened, because Sentry as a service lives off the ability to introspect the interpreter, to see what the interpreter is doing right now, to, if you get a traceback, to get as much information out of it as possible. So Python tracebacks, for instance, as a side effect of this, are really quite good. You can see what happens, you can see why, and you don't have to put external debug tools in. The language in itself is powerful enough to give you that information. So as where Python is going, there's obviously this big thing. Which one do you want to pick? There are two versions of it. The majority of what we have runs on 2.7. In fact, right now, nothing is deployed to run on 3.6, but we do have plans to actually move there. And you can see now that there is more and more reason to actually use Python 3 for certain things, in particularly asynchronous I/O. And this is happening. A lot more development is going on in machine learning environment, especially also with TensorFlow now, which lots of people want to use, which has strong Python, which basically is to a large degree Python. There is a reason for people to use the language. And if you want to build services in it and you plan on interfacing in that direction, it's a good pick. So the foundation of most software as a services is one framework. You can pick between multiple here, particularly if you're on Python 3. There's also AIO HTTP now. But you can also roll your own, which is not that much work. And then the question comes up, how do you actually structure your application for building a software as a service thing? And Python gives you a big choice in doing that. For me, the most important part about software as a service, which sounds a little bit like obvious, but might not have been to me a couple of years ago, is that security really needs to be a much stronger point in the application design than I initially thought it would be. And some of these patterns for actually bringing security to a more prominent part of the application, I think, are very universal and are not necessarily constrained to the code examples I have here, because the ideas are the same. So if you only want to take one thing away from this talk, it's context awareness, which for me is a security topic. And the idea here is that from anywhere in the code, you should be able to figure out what's your security context. And I don't know, how many here actually use Python for web development? Can you quick show of hands? How many here use Java? Okay, so it seems to be about the same number. How many here use Node.js? Not a lot. One test, how many here use C#? Okay, there are more C# users than Node users, which is impressive. So one of the things that you have with C# is you have a logical call context. So I don't know if you're aware of this concept, but it's the idea that code can actually propagate a hidden context from call to call. In Go, you would have to do it explicitly by passing a context object around. In Node, it's really very tricky. There is theoretically some support for doing that, but it doesn't really work that well. In Python, what most people do is they use context local objects, thread locals, and it's the idea that there is an object which contains information that you can access from anywhere, and then you can put stuff on there. And I was criticized for a long time for having thread locals as a first-class citizen in Flask. But my experience over the years is that strong thread local data or context local data is really important because it encourages you to build better security policies into the application that would be too much work otherwise or too easy to miss. The most important part there is tenant isolation. And to get this whole concept isolated down to its most primitive point is that a tenant represents in most applications one isolated customer. And it's often not called tenant, it's often called organization or whatever you have. And it's your little box that you give a customer, and the customer is not supposed to move out of this box. So each customer might have different resources which are contained in this box. And you don't want to accidentally, when only working with a bunch of resources, to touch the resources of another customer. So for software as a service applications that have multiple customers running side by side in the same process, which is usually what you do to save, to make it more scalable, is the idea that from anywhere in the code you should be able to figure out what's my current tenant, what's the current customer I'm working with. And by being able to do that, you can then automatically scope down a whole bunch of other things to assert in a central place that you're not accidentally giving access to stuff that the customer shouldn't have access to. So you can, for instance, build this idea that you can always get the current tenant for the current request, for the current context, which is the current thread or something like this. And if it's not there, you try to grab the tenant from information you have available. For instance, in Flask, you can do it this way, that you try to get the current tenant from the G object, which is thread local. If you don't have it, you will try to parse the request data to get the authorization header, to verify the authorization header with the database, and to then query for the tenant and store it. Which means that the first time you ask for the tenant, it will be cached on the thread local, and it will be initially populated from the data from the initial request. Or you can directly put it on the thread local data if, for instance, you're working with a salary queue or generally just a queue worker. You can always put the tenant initially when you start working on the task onto this thread local, and from that moment on, everything can work with this tenant only. So this is an example of one of the queries that you might have if you don't have proper tenant scoping, which is that there's a batch call which takes a bunch of projects by ID. It has some instructions in this changes object, and then you want to query all of those projects which are not currently invisible, and then call update for each one of those. Now, if this is coming from a user's API call, nothing stops the user from putting project IDs in there which are not belonging to his organization. So that's the part where it gets dangerous. And by having the ability to access the tenant from anywhere, you can actually change the underlying data layer to automatically scope to the tenant, or to automatically make sure that at least if there is no scoping to the tenant happening, that you give an error. So I know that this is something that happens very frequently, that people just don't restrict the queries well enough to untrusted user input. So obviously you could do it this way, that you go in there first and you validate that IDs only ever contains projects which are relative to the current tenant. But you already need to do the query to get the project in the first place. So people forget about this, or they don't want to do it for efficiency reasons, try to move it to a higher layer where it doesn't work. So if you have the information about the current tenant at all times, you can, for instance, change your underlying query system to take into account the tenant. So if you use, for instance, SQL Alchemy, which is a very popular Python SQL library, you can modify the default query to have an attribute on it which is called current tenant constraint, which by default is true. So by default, the query will be constrained to current tenant. And then you can have an explicit method called tenant unconstrained unsafe, which you will know if you call it, it's an unsafe operation, which will make a query which is unconstrained. And then you listen in on the event system, which the query system uses internally, to say, before you compile this query, if the query contains, it's down here, if it contains an object which has a tenant attached. So for instance, a project can have a tenant, an organization member or something. Any resource that exists within the application can have a tenant attached. And if there isn't a tenant and the query is constrained to the current tenant, you will just automatically filter this query down this way. So in this case, if you have then, so this is just some code to automatically attach a tenant ID, which is a column, which is a foreign key to your tenant, and then have a relationship set up this way. That whenever you mix this tenant mixin in, for instance, into a project, it adds a hidden tenant ID, which is then used to scope it down. So if you query for the project, it only gives you project 42 because that happens to be the only project which is available to the current tenant. However, if you do tenant unconstrained unsafe, it will give you the list of all the projects on the system. So I think that's something that's very easy to implement. even if you don't have a powerful data layer like SQL Alchemy, you can push almost all your data access through something that can take into account the current security context in a way. One thing that you have to be careful though is that in this case, the query object is always explicitly here. So the query class is set to the tenant query. So any class that will use the tenant-bound mixin now will actually use this constraint query. Back references which are set up by the system automatically will not do so. So this is why you have to be careful about specifically in Flask SQL Alchemy or SQL Alchemy that back references that are created by the system might be unconstrained. So there needs to be some, if you already have a system in place, it needs to be configured appropriately. For instance, in Flask SQL Alchemy, you can actually set the default query that will then be used by every part of the system. But this is not the only use you can have for this security context. An obvious one is at any point in time you can refer to what's considered the current user. So the current user is usually different from the current tenant. The current tenant can be an organization, for instance, or it can be one resource. It could be a current application, it could be whatever is the main resource type that your application has. But the user can actually, in some cases, be one that has access to multiple tenants at the same time. It could be a resource within the tenant. It's a good example, for instance, if you take Slack as an application, Slack has a user that belongs within a tenant. So if you have a Slack team, the user is always local to the team. Another example, however, is GitHub. GitHub has lots of different organizations which could be considered tenants. However, the user roams around the multiple tenants, and I can access multiple organizations as a result. So the user in this case is different. So you can actually have a user as a separate concept where you say, like, there's a user, but if there's no user, try to get it from a user session, try to get it from an authorization header or something like this. By setting this up in a central place, you can at any point in time refer to what is considered the current user. And you don't need to pass down this information explicitly, which means that even in a very, very far away system, you can always refer back to this information. Because one of the problems you have if you need to explicitly pass down this information is callbacks to systems you don't control yourself. So for instance, you might have an internet translation layer, which has one function call, which is like translate the string, but there is no ability to pass in the language. You might have the ability to pass in the language, but you don't. It might go through an API call where there is no ability for you to pass down context. By having the context as a thread local, you're always guaranteed at any point in time. You can refer back to this. Likewise, you can use this to restrict the access scope further down. So for instance, just because you have the current user does not mean that the user has given the current request or the current task the whole scope of its access rights. So a good example here, for instance, is API access tokens. Very often you want to give out an API access token to your user account to something else, which only has access to a subset of your system. So you don't want code to go in and say, like, give me the current user and then try to see what the user's access rights are. What you actually want to do is you want to have an abstraction in place where you can say, while the user is an admin, however, for this current request, the token only gives read access to his email address or something like this. So this is the standard scoping problem you have with OAuth, for instance. And by having the scopes on the context, you can provide different systems to restrict the scopes down. So for instance, you can say, like, I want to take the current user scopes, but roles as a scope, but I want to reduce the scope based on current authorization header or something like this. One other really nice thing when you have a security context in place is that you can use it to audit, to record audit logs from anywhere. Because any part of the system has access to this, you can just at any point in time provide a simple function that will attach as much information as available to an audit log. So for instance, if you change your email address or something, if there's an API call, for instance, to change the email address, the API, it can internally invoke log and then passes as an action, for instance, change password or something like this. And then it will grab from the security context and from all the information it has available as much information as possible to give you an audit log, a record in your database. So you can go in later and actually see what happened. This is very valuable if you have problems with even if you're unconcerned about security, the audit log is very useful for customer support because it can see what happened. Sometimes users do something like they delete a project. They don't realize until later that it was themselves that caused the problem. So by having the audit log, whenever you have a dangerous operation like deleting something or changing access rights, whenever you just log it out, and then you can create a database afterwards and figure this out. And this just lives off the security context because you don't have, very often you already have a system in place which manages access rights somewhere, and then there's no way to pass all this information in by having it in a central place. You can always grab it. So for instance here, if there's a request, we'll attach the remote IP address to it. So this log message might be contained in a utility somewhere, which is not even always executed when an HTTP request is here. In that case, there would be no IP address because request also here is a thread local. It's just very convenient, and Python really allows you to build more and more of those really little self-contained utilities, which just grab information from wherever possible. And obviously, if you have things that need to be translated, you can you can get the current language of what you want to have from different sources, and then you just need to get internally. You can always call what's the current language, and we'll try to figure out intelligently what the most appropriate language is. With Python, what's really nice is that you can design the system as you go. So it is very inviting to come up with a really clever overall design. It's like, I have done this like 3 times now. I really want to build this amazing new system which does it better than everything I built before. And you will spend a lot of time actually trying to make the basic system work before you get any work done in actually building the thing that you were meant to build. And because Python is a dynamic language, you can actually just start solving your problem and then build the nicer system around as you go. So this is actually something that Sentry did right. It started with Django as a framework, and it just became an application of sorts. And Sentry nowadays doesn't look anywhere what it looked like when it was created initially. It evolved over time in really interesting ways. But and obviously it's grown code. It has its own problems. It carries around some of the stuff that was decided 8 years ago that really didn't fit the design in any way. But it didn't hurt the maintainability of the code as much. So one of the things that is a counter argument that people bring against Python is that it's weakly typed, or at least it's dynamically typed. So there's a lot of checks that only happen as you run the code. The compiler, well, the lack of compiler doesn't tell you obvious mistakes. But it actually turns out that for a SaaS business, that's not really the concern because it runs all the time anyways, at least for as long as you have customers, so you spot regressions really quickly. However, the fact that it is dynamically typed actually allows you to build really elaborate shim layers to switch over internal systems to nicer designs and then eventually take out the shim layer. So you can actually just build something, and then once you know what your actual problem is that you're trying to solve, you can build a nice abstraction around it and then find a way to shoehorn your already existing system onto the nicer abstraction. And then when you have taken out all the old callers, you can just take away the shim. And that works really well as a dynamic language, and it would take you an enormous amount of effort to actually make work in a compiled language. To give you an example of the simple design ideas that we didn't have to change, Sentry at its core is still an unsharded Postgres database. So we didn't actually invest any effort in building a tremendous data routing layer or anything else because it wasn't really necessary for many, many years. And if we would have done this initially, we probably wouldn't be in a position where we are now. So it actually pays, it pays really well to start with a simple design initially and then evolve as you go. So that's, I think, the strongest point for Python is that it helps you start with a prototype and then move into production and then actually evolve it over time into the form that you want to the form that you want to have. When it comes to actually operating Python in practice, there are different forms of Python you can have. The most obvious one is called CPython. It's a standard Python language. And there's another one, which is PyPy, which is a Python written in Python in a very weird way, but eventually it spits out a garbage collected, JIT interpreted interpreter, which you can use as an alternative. And they both have their own up and downs. When it comes to operating the language, I think the main difference is the way they track memory. And this is also something that I find counterintuitive in many ways, is that ref counting in many ways is actually superior and by ref, CPython is what everybody uses as a start. And it uses ref counting as main source of memory management. But it has a cycle garbage collector to try to figure out if objects have circular references to each other, if it can break cycles. And if it can break the cycle, it will do so, and then the ref counting kicks in and will eventually clean up the garbage. This turns out to be a really good fit for a lot of web applications, because from start of the request to the end of the request, you don't leave around a lot of global state, which means that once the application is warm and running, your memory usage stays sort of constant. It goes up a little bit when a request comes, it does some stuff, and then eventually cleans it up again. Whereas with PyPy, you have a garbage collector as the only source of memory management, which for software as a service application can, with the same workload, often mean that your memory management behavior is weird and unpredictable. Obviously, you have the same problem with Java and many other languages, but Python, because it is already an interpreted language and it's quite slow and it has a lot of restrictions in place, the reference counting doesn't actually turn out to be a problem. In fact, it takes away some of the annoyance that the garbage collection will bring to you. However, at the same time, with PyPy, if you operate it specifically for the problems it's very good at, it can actually turn out to be very memory efficient for what it does. So for instance, if you build a service that handles many, many connections and wants to send messages to browsers or like WebSocket connections, something like this, you might want to try PyPy as an alternative, because it has really neat tricks to work with memory that core CPython doesn't have. Because core CPython has a very straightforward memory layout. Objects are really quite big, whereas PyPy can, in certain circumstances, figure out that an object doesn't actually have to be this big because all the uses of the object are of a certain type. So for instance, dictionaries which only contain string keys or are below a certain size can be represented better in PyPy. So that's one of the big differences in operating the different versions of Python you can have. Once you are operating Python, this is your most valuable piece of debugging primitive, which gives you access to the current interpreter frame. And that's something that's being abstracted by different tools. But effectively, what this does is whenever you call it, it spits out the current state of the current thread and in which state the interpreter is. So for instance, you can spit out all the local variables. You can figure out in which function you are. This is what is also being useful for when you have an error. You can actually go back your stack trace and figure out exactly which state everything is. And for as long as you're using CPython, calling this is actually surprisingly performant, because the interpreter is so straightforward that actually generating this information is free, or almost free. And so you can actually build really elaborate debugging tools that can run in production without sacrificing further on the performance that you have. So you live with not super fast language as a default, but then you can actually build really nice tools with it. So this is what started Sentry in many ways, is that the fact that you can dump out, for instance, one of the things you can build with this as a base, you can say like, request comes in, I want to start the monitoring thread now. I want to see that if this thing still runs in 10 seconds, please dump out the current stack trace to see where I'm hanging. So for instance, if you have really weird behavior where sometimes requests take for like 30 seconds and you're not quite sure why, you can build this really easily and then figure out where you're stuck. You can also do this for any other thread. It doesn't have to be the current thread. And obviously, you can also do this as a way to modify behavior in certain ways. So I built a tool a while ago where you can actually connect to already running CPython interpreter to then attach a debugger, run the CPython internal API to start a socket that's listening in on debugger calls. So you can actually run a Python shell to a already running process without having to change anything. And the fact that you can do this with the language is really convenient. So for instance, one of the things that you can sometimes see is that if you use Flask, for instance, and you have an error, it gives you an in-browser traceback, and you can expand any of those frames, and you can run local Python code to figure out in which state it is. So for instance, you can just run Python code and say, like, from Flask input request and give me the current request URL. So this actually, it holds the execution of your program, and you can just do stuff there, which is a huge time saver. But it doesn't only have to work locally. In fact, I had to put pin code protection in there, where the pin code is printed to your terminal, because it used to be unprotected by default, and people ran this in production, sadly. And then that was a very good way to get your data leaked, because you can just run arbitrary code, including open external debugging shells, and then SSH into your machine. So don't do that. But the fact that you can do it is really great. Obviously, you have the Python interactive interpreter. So if you have a good data layer like Flask for Alchemy or Django's ORM, you can just at any point in time spawn a shell and inspect your database with convenient Python objects. You can easily script it out. And it usually starts really quickly. So it gives you a huge performance, well, not performance, but it gives you a huge speed boost to your development. So if you have a bug in certain data, you can just use the data layer to test out, like, how do I have to modify it to fix up my data and stuff like this. So how do we structure things so that we enjoy development with Python? So for software as a service, you have, in our case, the idea that you want to deploy it as quickly as possible, especially if you push out a bug, you want to fix it. And be unable for developers to screw up this whole process. And if they do so, you want to go back as quickly as possible. And to give you a little bit of an idea of, like, what we're talking about here, in case of Sentry, this is probably 40, 50 servers that are running. So this is sort of the scope that we are looking at. So we want new developers in the company to be able to push out stuff without feeling like they broke the world. So from a human perspective, this looks like you commit. Someone reviews it, it gets integrated into master branch, and it gets deployed whenever the next thing goes out. So obviously this requires that there is a reasonable good testing coverage, and it also requires that your local development setup closely mirrors the production thing. And I think that's one part where a monolithic architecture turns out to be really nice. Sentry is not particularly monolithic, but we can replicate the entire setup that you have in production with some restrictions on concurrency and stuff like this on a local developer's computer without having to run, I don't know, Docker or something like this. It's great because it means that you're not going to commit something that only happens in production for the most part. And that helps new developers as well, because you get a local development setup within, I think, 15 minutes maximum. So you can actually, on the first day in the company, you can actually get stuff shipped. So to make sure that we are not checking in any garbage, we set up local Git commit hooks that actually run a Python linter. So that takes away the obvious one, like you forgot to import something, or you imported something too much. So we have a lint step that runs before you commit. That is a huge time saver. We actually built custom linters for this on the basis of Lake 8, which is one of the linting tools for Python. So we actually catch some of the things that we know are problematic in production. A good one is we disallow the use of the print statement or keyword or function, because it turns out that with aggregated logging and someone putting a print in a really hot code path, the log files are garbage. So that's an example of a custom linter that we put in place. So as our rule, we keep master stable, and then we deploy whatever is on master. And we build the system so that we can go back really, really quickly to an earlier deploy. So if someone does push something crappy to master, we can roll back within less than a minute. So how do we avoid downtime then? So we want to deploy all the time. The most important one is bidirectional compatibility of data. And I think that's the one that's the hardest to wrap your head around. But it's the idea that your data changes and your data query changes are separated by a long period of time. So we can actually roll out a schema change a day or two in advance. And then if it still goes well, we then eventually roll the code over that actually depends on a new schema. That simplifies rollouts, and it helps us go back if something goes wrong. In particular, also, it helps us with a situation where not everything runs the same code at the same time. So if you have 40, 50 servers, and you don't have a downtime to deploy a code update, it means that some of the servers will still run the old code but see the new schema. And if a rollback happens, then there will be new schema running and then all the old code. So by supporting this, separating this idea that old and new stuff can run at the same time and they can go back in both directions within limits, that becomes a core engineering principle, and then your life becomes significantly easier. So that's my personal opinion, but I think it makes a lot more sense to invest company money into fast iteration than blind scalability. If you have the scalability problem, you're doing something right with the company anyways, and then you can look at this independently. It's very unlikely that it will structure something in Python which you can't scale out at all. And if you have that, it's a nice problem to have, and you can invest into this separately. However, if you screw up your fast iteration times, it's a real problem. People get frustrated. Nobody wants to work on certain things anymore. In particular, if you have certain problems within the code base which are critical but really, really slow, and it becomes hard to actually change on them, they age really badly, and nobody's quite sure anymore how it works. So that is definitely something that we focus on. And I think duck typing in Python helps a ton. So if you have this part, this really frustrating core part in the language that in your project, which turns out to become a problem over time. We had a case where we had one of our source map handling. So if you use JavaScript, very often you have minified JavaScript files. So if you want to symbolicate them into like unminified files, we need to use source maps. They're huge JSON blobs. That used to be a very terrible piece of code. And it's just hacked in at one point. It was really slow and needed to be modernized. But we couldn't actually do it in one step. So we wrote a new and nice system that we wanted to have, and we just made some proxy objects to make the old path look into the new one, and it just worked out really nicely. And then we could eventually clean it up. So the fact that you can actually just make the language proxy out calls through other things is really nice. And the lack of types actually helps really well there. So to support the really quick release cycles, the one obvious rule is that large systems behave a little bit more like organisms. So you're not quite sure how they behave. So you might push a deploy to one machine, which has some effect on the others. So we just take it as a general rule. That's how it works, and we live with it. And as an extent of this, not everything that we run runs the same version of the code all the time. We try to contain that at least if we push out a new version, that each machine sees the same build. So we build it once, deploy it to all the machines, and then each of the machines are supposed to run the same thing. But we used to have the situation in the past where machines individually built their builds, and then some version pinning was done incorrectly, so some machine ran an older version of the code and so forth. Also, you have to take into account this a little bit, that for instance, dictionaries in Python are unordered. So if you have random hash seeding, one machine might have the dictionary written out in a different form than the other one, so it does stuff with your caches and things like this. So you have to be aware that there might be differences between the different nodes that you're running. You can contain it as much as possible, but at least during the deploy, you will definitely have the situation where not everything runs the same code. So because we deploy very, very quickly, we iterate very quickly, if we have huge features that we want to get out to customers, we break them up into tiny, tiny commits, and we feature flag them out, which means that we actually ship. If there's a feature that will take 9 months to go out, it goes in every day in little pieces and bits, and it's just disabled. It's not sitting on a branch. That turned out to be not a good idea. People don't review branches if they're too large, and then you merge this huge, tremendous thing in, and it breaks, and everybody's frustrated. So we just constantly ship stuff out. Then we try to make prod and dev look as close as possible. And one of the other things that we then have to deal with is that while we are a software as a service, we also have the ability for people to install it themselves on their own installation. So we need to make sure that what we ship to the customer doesn't contain half-broken code that they won't see. Or it's fine if they don't see it, but we need to make sure that we can actually make regular releases for on-premises customers. So the way we do this is there are 2 release cycles. One of them is all the time, and the other one is every 6 weeks. A release is tagged off for on-premises installation. And we just, when there's a work in progress thing, it's feature flagged away, you can't see it. And sometimes it happens that customers have stuff running, which is a developing feature, they don't know about, and then with the next update, it goes away because it turned out we didn't want to go finish this feature. So that's definitely something that we do. With the update process that the customer goes through with the on-premise installation, we might create database tables that are never used and then torn down again. So we actually implement this way. There's a class in the code. This doesn't look like this at all in Sentry. This is something I mocked up, but the concept is the same. It's a class that defines what the feature will look like. And the idea is that you have a key which uniquely identifies that feature. You have a scope which says, it's a function which says that this is for which this activation of the feature is scoped to. And then optionally you can enable it for like 50% of people, 90% of people by default. And then there's a default value, which is usually false. And so when you try to evaluate if the feature is enabled or not, by default you try to get the scope specific for what you're operating on. Then you try to see if for this scope and the key, it was explicitly set in the database, so you can force a user to have it on or off. And then if not, if it wasn't stored in the database, you just see if you should enable it randomly, and otherwise it's off. So this, for instance, allows us to build features like this. You can say 90% of users should be on the new sign-in flow, scoped on the request's IP address, for instance. And actually, this should be removed, disallow overrides. But the idea is that you can actually override it as an admin user. You can force an IP address to always have it and stuff like this. Or, for instance, users might opt into the new dashboard, in which case it's scoped to the current user. But if so the scope would be the current user. But then, for instance, the default is, it's by default enabled for all tenants after the 1st of 2017. So users which created the organizations after the certain date will have it on by default. Everybody else will have it off, or if they overrode it specifically in the setting, they will get it. And if the feature is just never enabled, then nobody will ever see it. And we actually do this so that we, for our own organization, so we use Sentry ourselves. For our own organization, we enroll ourselves into new features, so we always see what the current state of development is like, which has one disadvantage, which is really annoying. Sometimes it happens if you always enroll yourself into the latest features that you break the non-feature enabled flow, and then you will only notice if users complain. So it's a good idea to also see the stuff when the features are off. So for testing features, there's a wrap around it. You can see if the feature is enabled. This caches the feature. It can also prefetch variables if necessary. And it allows you to easy grab for if a feature is on. So you can do grab for is enabled, and you can see if the feature is on. For deployments, very quickly, we built Python wheels. Python wheels in this case are binary. It's just zip files basically containing binary code if you have one, otherwise just Python files. We put those zip files into Docker images and then just push it out. It's pretty straightforward. There's no magic involved, and you can make it more magical afterwards if you want with service discovery and so forth. But we try to keep at least the basic part just Docker images, and then just push it out. Yeah. So if you have questions, I'm happy to answer. And if you also want to ask questions specific, not to the talk, but to sort of the general Python ecosystem and how you can use it, just let me know.
I was thinking about the thread local variables, and do those make it more difficult to do unit testing when you're talking about incoming HTTP calls?
So that's definitely one thing that people say is harder. I disagree with it because I build tools for managing that state. However, it's definitely something where, so in Python, for instance, there's PyTest, which is a very good testing system. So if you use PyTest, you can enable fixtures where, for instance, say like I want to have a request, and then the code that manages the fixture will set up the thread local appropriately. So by just saying this code involves the request, it will manage this hidden state for you. Likewise, in Flask, for instance, you can the thread locals are managed through an abstraction layer called the application context, which you can, with the Python with statement, create and destroy, which makes it quite straightforward to manage in tests. So I think the moment you understand this is how the context works, it doesn't actually make tests harder. But you need to understand that this is what's happening. And I think that's something that trips over new developers, definitely.
This may not be directly related, but I think it's within the Python ecosystem. So do you have any opinions about like the various asynchronous I/O frameworks Python has, such as like G-Event and Twisted and what else?
Yes, but it's complicated. So the thing with asynchronous I/O is that for the most part, I don't see the use of it for the use that other people see. A lot of people want to see that you can use asynchronous I/O to have like gazillions of connections to the client. That's something I really don't think is in any way useful because, well, I will go into this detail later, but for that part, like managing a lot of connections to the client, which is what Twisted does and stuff like this, I personally don't care. What I care about is like having, for instance, you have a Cassandra database cluster or a React database cluster or Redis, lots of Redises, and you want to send a database query to lots and lots of those, and you want to wait until all the results are coming back. That's a part where asynchronous I/O I think is very useful in Python. And that for a long time didn't really have good answers. And with Python 3.6, you can actually build this on top of the native async I/O layer. So I think that will be interesting. And I've also heard from other people that for that particular use case, that's going to be interesting. The reason why I don't care that much about the connections to the client is that I deploy often, or I like to deploy often, so I don't want to deploy the code that terminates the connections to the client. So I try to, from an architectural point of view, move the client connections to a separate hub, which only deploys whenever the hub needs updates, and the hub then uses a communication layer like a queue or something like this to talk to the main application part. So for instance, if you have a WebSocket connection going to the client, and you use it to notify the client about new comments coming in or like a little bubble of notifications, you write your code normally as you would always do, and as a side effect, you publish an update like the user that is listening in on this channel will now get a message coming up in the messaging queue. And then you can isolate the messaging queue into something that's really good at asynchronous I/O. Sorry, not the messaging queue, but the hub that talks to the client, which keeps the WebSocket connection open, in something that's really good at asynchronous I/O. And you could actually write it in Go then, if you want, for as long as it talks with something that Python can also talk with. So that's why I don't have a horse in the race which async I/O framework is interesting, which build like HTTP layers and all that sort of stuff, because that's just not really my concern. But I'm very interested to see how like talking to a smaller number of I/O things will look like database layers, or like just talking to a database. And I think asynchronous I/O, async I/O in Python 3 will be quite interesting, because it doesn't have this strong, one of the problems that you had in the past was you either had greenlets, which made it work, and they monkey patched the world, and then it was very hard to do this isolated test case where you have lots of blocking code, and then you have this one little piece of code that wants to do async I/O. So that didn't work really well with that. And then all the other frameworks were so opinionated and world scattering that it was very hard to integrate for other reasons into this code. With async I/O, I think there's a chance we can start. From this call, async starts, and then it stops again.
This is also mostly related to the Python ecosystem. I'm just wondering your take on the GILLOC implementation and threading in Python. If there is a good way to, it's a well-known issue that it doesn't scale good on several cores with the GILLOC. Is there any, do you know if there is any other work been done that for a new implementation of Python that they try to solve it, or what's the best take to if there is any
I have very low expectation in that ever being a solved issue. I think it will never be solved. I also don't really think that for the case of building web applications, it's something that needs solving, because you saturate the cores anyways by just spawning lots and lots of your processes. It really only becomes a problem if one specific process needs to have concurrent stuff. So I think for web in itself, it's not nearly as much of an issue as it is for other environments. And the problem you have with killing the GIL is that you can kill it. It will just get really slow, because then you have to do per object locking. So it's possible to do that, just nobody wants to do it. And then even if you do kill the GIL, a lot of code will break, because it takes certain assumptions about the GIL that are currently in place, which are impossible to guarantee. So that's why I think my hopes are not very high that this will be solved. I do see the possibility in the future to restructure the Python interpreter to support multiple threads and independent interpreters in the same process. So I think that might be possible, where I do message passing between them. So each local interpreter would still behave exactly as it does today, but you could then make little, like Erlang style threading in a way. I think that could be possible.
Yeah.
It's not happening right now.
Yep, thank you.
Hi, we were looking at using feature flags. We haven't really delved into doing it yet, because we were concerned, would you end up with just loads of if statements throughout your code saying if this framework, if this feature is enabled, then do that? Do you find you have loads of them?
You mean that features are there that we kill features, so it's not like it's there. We try to have features separated so that they don't touch too much of the code. So in particular, if it's very rare that you have, so the only part where I actually know where we have this if feature is on, if feature is on, if feature is on, is our navigation bar in the project settings, because we only show the button to configure certain things if the feature exists. So that's actually the only part where I know where we have this, that we do these feature checks that regularly.
Makes sense, yeah.
And we definitely kill features. The moment it's on by default for everybody, the feature will be taken out. All right. Thank you very much.